Good morning, everyone. Welcome back. Good to see you again. So today we're going to be talking about polynomials. And polynomials is not too tricky of a topic, so that's why this session is a little bit shorter. This is only going to be an hour and a half to 2 hour session. But it is important for a lot of different topics kind of across the IB. It's going to show up like we saw the other day when we're doing rational functions. It's relevant for oblique asymptotes. It shows up a little bit when you do Maclaurin series. If you ever do division of Maclaurin series, you need to be very comfortable working with these terms. And in general, it can always show up as its own question about the sum and product of roots, or maybe the factor theorem, or something like that. Okay, so with that said, I'm just going to set up the slides and then we will get going. Okay, so before we talk a lot of details about polynomials, it might be useful to define what a polynomial is. And a polynomial is a combination of positive integer powers of x. So it's a function that I can write in the form some constant an times x to the n plus an minus 1, x to the n minus 1, and so on and so forth, okay? So it's only going to have powers of x, and that can include x to the power of 0, okay? It can be, then that would give me a constant term. In IB, we don't include functions that have like a 1 over x or x to the power of minus 1. We're only dealing with positive or non-negative integer powers of x. And I can write the polynomial in a summation with summation notations by saying I have the sum from k is equal to 0 up to n of the kth coefficient times x to the power of k, basically. All right. And one important term for polynomials is what we call the degree of the polynomial. And that's basically just the highest power of x that appears in the polynomial. Now, usually that will be the first term in the polynomial. You can look at the first power of x, but sometimes questions will deliberately try and trick you by putting the highest power somewhere that's not at the beginning. So you have to be careful. So if I was trying to find the degree of 1 minus x cubed plus 5x to the 7, the degree would be 7, because 7 is the highest power of x that I have. An important skill that you need to be able to use is identifying specific terms in a polynomial. So if I ask you to find the x to the power of 6 term in a polynomial, that means I want you to pull out the term that has something times x to the power of 6 and tell me what that is. And similarly, if you're asked for the coefficient of the x to the k term, you want to pull out just the number that's multiplying x to the power of k. So for example, let's say we want to find the coefficient of x to the 0 and x to the 4 in 3 plus 2x plus 3x to the 5. So x to the 0 is 1, corresponds to the constant term. So the coefficient of x to the 0 is just this 3, all right? And then there's no x to the 4 in the sum, so the coefficient of x to the 4 is 0, all right? Now, if you're multiplying two polynomials together, then their degrees are going to add, okay? Because when you expand out the polynomial, if you start by just expanding the highest powers of x, they're going to multiply together, and you're going to have one term which has a times b something times x to the power of n plus m. And all the other terms are going to be smaller because this is already the product of the two largest terms in each of the polynomials. So let's say I have 2x minus 4x cubed plus x squared, and I multiply that by x to the 7 plus 3x to the 8 minus x. Okay, when I do that, I have a degree of 3 here and a degree of 4 here, so I add those together and I get 1. A degree of 3, a degree of 8. Sorry, I don't know why I said 4. Okay. Now, time for our first little exercise. I'm going to give you guys a minute to do this while I grab my iPad. Okay, so it looks like most of you got this, so I'm going to go over it now. So if P, Q, and H have degrees 5, 6, and 7, respectively, then P times Q is going to have a degree of 5 plus 6 is 11. And then H squared is going to have a degree of 7 plus 7 of 14. Okay, so this one is bigger than the other one. So actually, the P times Q is not going to affect the degree at all. And I'm just going to have H of x squared times x cubed. And that's going to do 14 plus 3 is equal to 17. And that's option number 3. Now, I mentioned this a little bit, but if we're looking for a specific term in a polynomial, remember that that is the term associated with a certain power of x. And when we have a product of polynomials, it's possible to find the coefficient of a specific term without expanding out the entire product. And this is an important skill. It shows up on IB questions in the binomial expansion, a little bit in Maclaurin series, and so on, right? So it's very important that you understand this skill. So let's say I'm trying to find the coefficient of x cubed in this expansion, 2x plus 3x squared plus x cubed plus 4x4 times negative 3x plus x squared plus x cubed minus x to the 4. All right, so I don't want to expand all of this out. That's going to be really annoying. Instead, what I'm going to do is realize that I can either get x cubed from doing 2x times x squared or 3x squared times negative 3x. And that's it, because if I picked any of these terms, everything over here is x or bigger, so that's going to give me x to the 4. So these are the only two pairs of terms that can multiply to give me x to the power of 3. And in general, you're going to have a relatively small number of terms that can multiply to a specific coefficient. And the question will just be set up that way because it's designed to make this, somewhat feasible, okay? So if I do each of those, this one gives me a 2x cubed, and this one gives me a negative 9x cubed. So in total, I'm going to have negative 7x cubed, and my coefficient is negative 7. All right? The coefficient is just the minus 7, not minus 7x cubed. You probably won't be penalized on an exam if you wrote down negative 7x cubed, but I do think it is safer if the question says coefficient to just say minus 7. Or at least put a box around the negative 7 like I did here. Okay, your turn. I'm going to give you a minute for this. What do I have here? I'm looking for the coefficient of x to the 4 in the expansion of this whole thing. And I'm not going to expand this all out. Instead, I'm going to think about which pairs of terms could give me x to the 4. And I'm going to look at these terms because they're a little bit simpler. I'm going to ask, what can I multiply 1 by that's going to give me x to the 4? Well, if I did 1 times the 5x to the 4, that would give me x to the 4. Then what do I multiply the x by? Well, if I multiply the x by 4x cubed, that's going to give me x to the 4 as well, and the 2x squared with the minus x squared, okay? So what are each of these going to give me? I'm going to have minus x to the 5x to the 4 times 1, and then I'm going to have 4x cubed times minus x, and then I'm going to have 2x squared times minus x squared, okay? So this gives me minus 5x to the 4 minus 4x to the 4 minus 2x to the 4 is negative 11x to the 4, and so the coefficient is just the minus 11. All right. Now, another important property of polynomials is that if two polynomials are equal to each other for all x, and they're not just intersecting at a particular x, that means that all of their coefficients have to be equal, okay? So if I have ax squared plus bx plus c is equal to 2x squared plus 3x minus 1 for all x, then I know that a is equal to 2, b is equal to 3, and c is equal to 1, okay? So, for example, let's say I know that ax plus b times x squared plus c is equal to 2x cubed plus 5x squared plus 2x plus 5. If I were to expand all of that, I would get on the left-hand side ax cubed plus bx squared plus acx plus bc. And that's supposed to be equal to 2x cubed plus 5x squared plus 4x plus 10 for all x, okay? And that means that I can match the A with the 2, I can match B with 5, and I can match AC with 4, and BC with 10. And if I solve each of those, first I find A is equal to 2, and then that means that B is equal to 5, and then AC is, and I solve for all of the other variables like that, okay? All right, let's go over this. So I'm going to expand what I have on the left-hand side, and I'm going to end up with AX cubed, and I'm going to have minus 2AX plus plus ACX, then plus BX squared, and this is supposed to be 2AX squared, sorry, plus BX squared minus 2BX plus BC is all equal to, I'm putting a triple equal here because it's equal for all x. 4x cubed plus 2x squared plus 50. Okay, and let me now collect the terms that I have together. I have ax cubed, and then for my x squared terms, I have plus b minus 2a x squared. Then I have plus ac minus 2b x plus bc. And it's all supposed to be the same as 4x cubed plus 2x squared plus 50. Okay, so the first thing I notice is that a is equal to 4. Just by equating the first two terms together, a is equal to 4. And then b minus 2a now becomes b minus 8 is supposed to be equal to 2. So b is equal to 10. And then next, I know that ac minus 2b, which is now 4c minus 20, that's supposed to be equal to 0 because there's no x. There's no x here. And so that's supposed to be equal to 0. And that means that c is equal to 5. All right. And therefore, I'm looking for a is equal to 4, b is equal to 10, c is equal to 5. That's option number 4. All right. As promised, we're moving pretty quickly. I want to talk about everything about polynomial division now. So a little bit of how you actually do division. You don't actually need to know all that much for IB in terms of how you actually do long division. We're going to talk about degrees of quotients and remainders, how to find remainders, and then the remainder and factor theorems, okay? So when I do polynomial division, it's essentially we're imagining doing a multiplication in reverse, all right? So if I were to expand out 2x cubed minus 3, 2x squared minus 3 times x minus 2, and then I added 7, I would get this polynomial, all right? And I can kind of reverse that process by writing 2x cubed minus 4x squared minus 3x plus 13 divided by x minus 2 is going to be 2x cubed minus 3 plus 7 over x minus 2. All right. All I did really here was divide both sides by x minus 2. And in this polynomial division, we call 2x cubed minus 4x squared minus 3x plus 13 the dividend, the thing that's being divided. X minus 2 is the divisor. The result, 2x squared minus 3 is the quotient, and 7 is the remainder, all right? And in general, we can write my, p of x divided by the divisor of x is equal to the quotient plus the remainder divided by the divisor. But usually, it's more interesting to write it in the form, the p of x, my polynomial, can be written as q of x times d of x plus some leftover remainder of x. Okay, and this form might look a little bit obscure now, but we're going to go over an example in a second. So you are supposed to technically know how to do long division, and the real question where I've seen this come up is finding the oblique asymptotes of rational functions. And I think there's a better way of doing it, but I'm still going to show you this process in case for some other reason you like it or it shows up on the IB, okay? But I want to imagine dividing 11x squared minus 26x minus 35 by x minus 5. What do? I first look at my leading terms. I have an 11x squared and I have an x. And x can fit into 11x squared 11x times. So I write 11x up here. And it might be useful actually if I write this separately on the right so you can see all of the steps. Okay, so I have over here, and I'm going to do something like this, x minus 5, and then 11x squared minus 26x minus 35, okay? First thing I notice is the 11x squared compared to the x minus 5. That means I can fit 11x's into, I can fit x minus 5 into 11x squared 11x times. Now what do is I subtract, I do 11x times x minus 5 is equal to 11x squared minus 55x, and I subtract that out. So I do minus 11x squared minus 55x, and then I make a line here for the result that I'm going to have, which is going to be, I'm going to have 0x squareds, then I'm going to have 26 plus 55, because I have minus minus there. That's 55 minus 26, and being careful, that gives me 29. So I'm going to have 29x minus 35. And now I repeat the process. I look at the leading term. I have a 29x and I have an x. X fits into 29x 29 times, so I write plus 29 here. And then I write over here, I do 29 times x minus 5 is equal to 29x minus, and 29 times 5 is, it's 100 plus 45, so minus 145, okay? And therefore, I'm going to subtract out 29x minus 145. And that's going to give me 0x, and then negative 35 plus 145 is 110, okay? So what do I write here as the result? I can say that 11x squared minus 26x minus 35 is equal to x minus 5 times 11x plus 29, and then a remainder of 110, okay? Now, I do want to show you a way that I find better of doing these, because again, in the IB, the only context where you need to do polynomial division is when you have something like, I'll just do this example, 11x squared minus 26x minus 35 over x minus 5. And you are trying to write it in the form ax plus b plus c over x minus 5. And you're trying to do that because we want to find the oblique asymptote of the rational, which is at ax plus b. And there's a much easier way to do this than the polynomial division, which is just to know that since I'm going to be in this form, I can actually work backwards, and I can write that form I can put it back over a common fraction and solve for a, b, and c quite easily. So if I did that, I'm going to do it maybe over here so I have a bit more room. I'm going to say I have ax plus b times x minus 5 plus c, and that is being divided by x minus 5, okay? And that's supposed to be equal to 11x squared, blah, 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 minus 26x, okay? So let's expand the numerator there, and I'm going to have, just because I'm not sure if you guys can see the screen that low, I'm gonna go up here. You should be able to see it here. And then I'm going to have ax squared, then minus 5ax plus bx minus 5b plus c all over x minus 5. Okay, so, and that's supposed to be equal to, in the numerator, 11x squared minus 26x minus 35. And that makes some things easy. I immediately can see that a is equal to 11. Okay, and then if I collect the x terms, I have negative 5a plus b x. That's supposed to give me 26. Okay, so negative 5. Now I know that a is 11, so that's 11 plus b is equal to 26. Okay, so b minus 55 is equal to 26. And that means that b, sorry, there's supposed to be a, is there a minus sign I'm missing? Yeah, there's a minus sign. It's negative 26. That's negative, negative, and that means b is equal to 29. And that's the same 29 that we found here. Now, what's nice about doing it in this form is that when you're actually working to find the oblique asymptote of a linear rational, once you get to, once you have a and b, you don't actually care what c is. Nobody cares what c is. It's not going to do anything. So you would actually just stop. You could stop your process here, and you found that your oblique asymptote is at 11x plus 29. All right, 11x plus 29, not equals. Okay. If you did want to find c, it's relatively easy now. I just do this negative 5b plus c. That's supposed to be equal to negative 35. And I now know that b is 29, and you can solve for c, and you'll find 110 as well. Okay, so whichever method you prefer here, either kind of working backwards from the fraction or trying to do the polynomial division, both are fine. This is the only kind of polynomial division that's ever showed up on the IB. Okay, let's continue. All right, I'm going to give you a chance to do this. I'm probably going to give you a minute and a half for this one, okay? So I'll set the timer now. Okay, so I'm trying to express this fraction, negative 5x squared plus x plus 1 over x minus 4 in the form ax plus b plus c over dx plus e. Okay, so here's some things I already know. I know that dx plus e is going to match the x minus 4. So it's just going to be x minus 4 in the denominator here. And I already know that the a is going to come from negative 5 over 1 is going to be negative 5. So I'm going to have negative 5x plus b plus c over x minus 4. Okay, I just need to solve for b and c. What I'm going to do is I'm going to write that over a common fraction. I'm going to say negative 5x plus b times x minus 4 plus c, and I'm going to leave that over the same denominator, x minus 4. Now, if I expand the numerator, I'm going to get negative 5x cubed. Then for the x squared terms, I'm going to get, sorry, not x cubed, x squared. For the x terms, I'm going to get plus 20x plus bx, and then we're going to have minus 4b plus c. And I'm sorry, that's a little bit close to the edge. It's getting cramped. Okay, and still being divided by x minus 4. Now, if I look at the original quadratic, I have negative 5x squared plus x. And over here I have 20x plus bx, which means that 20 plus b should be equal to 1, which makes b equals to negative 19. All right. And then to find c, I notice that I have negative 4b plus c is supposed to be equal to 1. And now I know that 4b that b is not negative 19, I can write this as 4 times 19 plus c is equal to 1. And 4 times 19, that's 38, 76. So 1 minus 76, c is going to be negative 75. All right, so my result is negative 5x minus 19 minus 75 over x minus 4. Now, this is a sort of subtle concept that often goes ignored in teaching, I've found. And it's not something that you like necessarily explicitly need to know. It's just that there are going to be questions where if you are not aware fundamentally of how the degrees of the quotient and remainder relate to each other and to the degree of the polynomial, it's going to be very difficult to know how to start the question. But it's not, you're never going to be asked expressly what is the degree of the remainder. But it is going to be important to know how the form in which I can express the remainder in certain questions. And we'll see an example of that later. Okay, so remember that polynomial long division stops when we were doing our long division earlier. We stopped when we were left with 110, which was no longer divisible by x minus 5 because there's no x's left. Okay, so we stopped the polynomial division when the degree of the remainder is less than that of the divisor. And as long as the degree of what I have is bigger than or equal to the degree of the divisor, I can keep going. All right? And since the degree of a product of polynomials is the sum of their degrees, then the degree of the quotient and divisor must add up to the original polynomial. So p of x is equal to q of x times d of x. That means that these two, q and d, when multiplied together, have to give the degree of p. So remember that multiplying two polynomials together, the product will have a degree which is the sum of the two degrees. So the degree of q plus the degree of d is equal to the degree of p. And the remainder, well, we said that the remainder is it's what we have when we stop the polynomial division, which means that we have a degree that's less than the divisor. We don't know if it's 1 less or 2 less, because sometimes we're going to have no remainder, we're going to have perfect division. But in general, the degree of r is always going to be less than the degree of d. Okay, let me put that into a specific example. If I have the polynomial 5x to the 9 minus 3x squared, and I divide by 4x cubed plus 3x, then the degree of the dividend of what I'm dividing by is 9, and the degree of the divisor is 3. So that means the degree of the quotient is going to be 9 minus 3, or 6. And then the degree of the remainder has to be smaller than the degree of the divisor. So the maximum possible degree it could have is 2. Okay? And if you did out the specific division, you would find that the remainder is something of the form ax squared plus bx plus c. And a or b or c could be 0, or they could all be 0. I don't know. I haven't actually done this specific division. It doesn't look like either of them, any of them are going to be 0, but still. But in general, this is the form the remainder is going to take. If it had a cube in it, then I could divide it again by 4x cubed plus 3x. And then it wouldn't actually be the remainder. Okay, so the remainder has to have a power of x less than the divisor. All right, your turn. I'm going to give you a minute to do this. Okay, let's go over this. So I'm dividing a polynomial with degree 6 by a divisor with degree 3. Okay, and I'm being told the result can be expressed in the form q of x times x cubed minus 2x plus some remainder r of x. Okay, so the degree of q, remember, when I multiply q and x cubed minus 2x, I have to get something with x to the power of 6. So that means I realize that q has to have a degree of 3 so that its highest term multiplied by the highest term of x cubed minus 2x gives me something x to the power of 6, specifically 5x to the power of 6. And that means that q has a degree of 3. Okay? Now, to find the maximum possible degree of r, I remember that when I'm dividing by x cubed minus 2x, I stop my polynomial division when the result that I have has a degree that's less than that of the divisor. If I had x cubed or greater, I could divide again. I could pull out one more term, and that means that the remainder cannot have a degree of 3 or higher, which means its maximum possible degree is 2. Okay? Now, we're getting to the real sort of bones of the topic. The sort of most important thing that's introduced in IB in the context of polynomials are the so-called factor and remainder theorems, all right? So I want you to notice that if x minus a perfectly factored p of x, that means it divides it with no remainder, then I can write p of x is equal to the divisor or the dividend, or it should actually be q of x times x minus a, okay? Then Notice that if I let x be equal to a and I find p of a, then I'm going to have d of a times a minus a, and that's going to be 0. All right. And this works for any factor x minus a of the polynomial p of x. And what that means is that if x minus a is a factor of a polynomial, then p of a is equal to 0. And that kind of makes sense. We almost already know that. I know, for example, that if a quadratic has a factor of x minus a, then it means that it's going to be 0 when I plug in a. So it's something that we already know. It's essentially the connection between a factor and a root. And it's just a consequence of the fact that multiplying anything by 0 is going to give me 0. Okay? But here's an example. For what values of k is x plus 2 a factor of 3x cubed minus x squared plus x minus k? Okay, so the factor theorem states that x plus 2 is a factor of 3x cubed minus x squared, etc., when x is equal to minus 2. Okay, so the polynomial must be equal to 0. Okay, so if I plug in minus 2, I'm going to get 3 times negative 2 cubed minus negative 2 squared plus minus 2 minus k is equal to 0. And that simplifies to k is equal to minus 30. Let's do an example. I'm going to give you a minute to do this. All right, let's go over this. So if x plus 2 is a factor of this cubic polynomial, it means that if I plug in negative 2, the polynomial has to evaluate to 0. So specifically, 3 times minus 2 cubed minus 6 times minus 2 squared plus negative 2 plus k is supposed to be equal to 0. Okay, negative 2 cubed is negative 8, so 3 times negative 8. And then I'm going to have negative 2 squared is 4, so minus 6 times 4 minus 2 plus k is equal to 0. And let's evaluate everything I can. I have negative 24 here, negative 24 again, minus 2 plus k is equal to 0. So negative 50 plus k is equal to 0, which means that k is equal to 50. All right, and let's plug that in. K is equal to 50. All right, the slightly harder theorem is the remainder theorem, right? Okay, so in general, x minus a is not going to be a perfect factor of p of x. Instead, we can write p of x is equal to some quotient times x minus a plus some remainder. And notice here I didn't put remainder of x because I know that when I'm dividing by x minus a, which is a degree of 1, the remainder is going to have a degree that's less than that of the divisor. So the degree of r is less than 1, means it's a degree of 0, and that means the remainder is constant. It's going to be a number, okay? Now what happens if I let x equals a again? I evaluate p of a, and I get q of a, sorry. It's not going to make a difference. And it's going to be multiplied by a minus a, which is still going to be 0. And then all I'm left with is the plus r. And then that gives us this remainder theorem, which is a generalization of the factor theorem. And it says that the remainder, when p of x is divided by x minus a, is p of a. Okay, so you take the negative of whatever's in there, and you plug it into the polynomial, and that gives you the remainder. Let's look at an example. Okay, I'm going to give you another minute to try this on your own. Maybe 30 seconds. Okay, let's go over this then. So I want to find the remainder when this cubic polynomial is divided by x plus 2. I know that the remainder theorem tells me that the remainder when the cubic polynomial is divided by x plus 2 is going to be whatever the polynomial is at minus 2. I'm just going to name it p of x here because it's not actually named in the question. So p of minus 2 is going to be 5 times negative 2 cubed minus 4 times minus 2 squared plus 8 times minus 2 and then minus 1. Let's evaluate all of that. It's minus 5. Not minus 5. It's 5 times minus 8. Okay. And then minus 4 times 4 minus 16 minus 1. So that's negative 40 minus 24 minus 16 minus 1. And is there a mistake here somewhere? Something seems off, but maybe not. This is going to give me a different answer from everything that I found here, which is a bit weird. Oh, yeah, it's because I'm an idiot. 4 times 4 is not 24, it's 16. Okay, that makes a big difference. So I have negative 40, and then minus 32, minus 1, negative 33. It's negative 73 is my answer. Okay. All right, our first kind of IB problem now, exam style problem. So I'm considering the function g of x is equal to x to the 4 plus 2x cubed plus px squared plus qx minus 4. So I have two unknowns. I have p and q in there. But I'm told that when g of x is divided by x minus 1, the remainder is negative 12. And when g of x is divided by x plus 3, the remainder is 20. So what does that mean? It means that if I plug in 1, if I evaluate g of 1, I should get negative 12. That's what the remainder theorem says. And so I can plug that in. I can say it's going to be 1 plus 2 plus, because all the x terms squared or cubed are just going to be stay 1 plus p plus q minus 4 is equal to minus 12. All right, so in other words, p plus q minus 1 is equal to negative 12. So p plus q is equal to negative 11. Now I can do something similar for x plus 3. So I can say that 20 is equal to g of minus 3, because remember, you have to look for the x that makes the factor 0. So g of minus 3, that's going to be equal to negative 3. This one's going to be a bit hard. Negative 3 to the power 4 plus 2 times negative 3 cubed. Then 3 squared is just going to be 9, whether there's a minus or not. So plus 9p, then minus 3q minus 4. It's equal to 20, all right? Negative 3 to the power 4 is 81. This is minus 27 times 2, so minus 54. Plus 9p minus 3q minus 4 is equal to 20. Let's simplify as much as I can. I have 81 minus 4. That's going to be 27. I'm going to subtract 4. That's going to be 23. So 9p minus 3q is equal to 20 minus 23. That's negative 3. Okay, let's write the system I have over here. P plus q is equal to minus 11. And 9p minus 3q, 9p minus 3q is equal to minus 3. That's my system. All right. How am I going to solve this? Well, I'm going to take the first equation, first I'm going to take the second equation and divide everything by 3 and say that 3p minus q is equal to minus 1. And then if I add p plus q is equal to negative 11, I'm going to end up with 4p is equal to negative 12. And that tells me that p is equal to minus 3. And I can plug that back into p plus q is equal to minus 11 and find that q is equal to minus 8. So those are my answers. Now, something slightly harder. I'm going to give you 5 minutes again because we do have plenty of time today. Okay, I think it's enough time. Let's go over the solution here. So I'm told that x plus 3 is a factor of p of x, and that p of x leaves a remainder of 6 when divided by x plus 2. And we are trying to find the remainder when p of x is divided by x squared plus 5x plus 6. So let me just write out what I'm trying to find. I have some polynomial, p of x, and I can write it as some quotient of x times x squared plus 5x plus 6. And it's going to leave some remainder, right? And that's the remainder that we're trying to find. Now, let's remember what we know about the degree of the remainder. The degree of the remainder is always less than the degree of the divisor. So that means I can write r of x, the remainder, as ax plus b, because it can't have an x squared. So it's going to be ax plus b. And either or both of a and b could be 0. But in general, there's going to be no x squared, so I can write ax plus b. And what I'm trying to solve is for the values of a and b. All right, so let's think about what we know. This quadratic, x squared plus 5x plus 6 is equal to 0, factors as x plus 2 times x plus 3. And isn't that a coincidence? It's exactly the factors that were given in the question. Okay, the question tells us that p of 3 is a factor, so if I plug in minus 3, I should get q of x times, and since x plus 3 is a factor of this quadratic, that's just going to be 0. And then I'm going to have plus a times minus 3 plus b, and that should be equal to 0 because negative 3 is a factor of the whole thing, which means that b is equal to 3a. That's my first equation. Okay, now I use the fact that p of minus 2 is supposed to be equal to 6. That's the remainder. P of minus 2 is equal to q of x, again times 0, because negative 2 is a root of the quadratic. Then I'm going to have plus a times minus 2 plus b is equal to 6. So my second equation is b minus 2a is equal to 6. But I know that b is equal to 3a, so I can say that 3a minus 2a is equal to 6, which means that a is equal to 6, and that makes b equal to 18. All right? So my remainder, oh, I shouldn't box that because that's not exactly what we're being asked. The remainder is 6x plus 18. Okay? So let's look at the quadratic and notice that, first of all, the product of my roots, is going to be negative 1 to the power of 4 times 4 over 2, and that's just equal to 2. All right, and the sum of the roots is just going to be negative p over 2. Okay, and that's as simplified as I can get it. And now I have the factor x minus 1 squared, and I have the factor x plus 1. Okay, so here is, I think, the tricky part, which is to realize that if I have x minus 1 squared, then I actually have two factors x minus 1. So I have two roots at x is equal to minus 1. I have a double root, which means when I add up my roots, the sum of my roots is going to be 1 plus 1 again, and then minus 1 plus the unknown root that I'm looking for, which I can call alpha. And that's all supposed to be equal to 2, right? Now I did 1 plus 1 because of this double root at x is equal to 1. And I want to sort of maybe reassure you that this is not something that has showed up on IB. They never have put a double root where you have to know the sum and product. But I want you to know it in case they decide this year to change that and to now ask you a question with double roots. Okay? So if I have 1 plus 1 minus 1 is equal to alpha, what does that mean? It means that 1 plus alpha is equal to 2. I'm just going to double check, though. Is there something I said wrong? Oh, sorry. That was the product of the roots, not the sum of the roots. But still, makes no difference. 1 times 1 times minus 1, alpha is equal to 2. Okay, and that means that alpha is equal to minus 2. Okay, and in this case, because it's the product, it wouldn't have mattered whether you took the double root or not. So even if you forgot that was a thing, you still would have gotten this right. So the last root is alpha is equal to minus 2, which means that polynomial can be expressed as p of x is equal to 2, because I have a leading factor of 2, then x squared minus 2x plus 1, and then x plus 1, and then x minus 2, or x plus 2 for this new factor that we found. Now, we could either plug in all these roots that we know and solve for p, q, and r with like simultaneous equations. I think it's easier at this point to honestly just expand this. So I'm going to write it as 2 x squared minus 2x plus 1 times x squared plus 3x plus 2. And then it's not honestly that terrible of an expansion to do. So I'm just going to do it, and I'm going to get 2 times x to the 4. Then for x cubed terms, I'm going to have one of those and one of those. So it's going to be plus 3x squared minus 2x squared. Plus x cubed. That's what I have next. And then after that, for my x squared terms, I can do either that, or I can do that, or I can do that. And so adding those together gives me 2x squared minus 6x squared plus x squared is minus 3x squared. Okay. And then for my terms in x, I'm going to have my terms in x, I'm going to have either 2x times 1 or 1 times that. Those are the only two pairs that give me 2x. So it's going to give me negative 4x plus 3x is just going to be negative x. And then finally, the constant term is just plus 2. All right, so all in all, if I expand everything out, I'm going to have 2x to the 4 plus 2x cubed minus 6x squared minus 2x plus 4, which means that p is equal to 2, q is equal to minus 6, and r is equal to minus 2. All right, checking for questions, but it seems like we're good. But the sum product of roots is next, so maybe we'll come straight back. So when I expand a polynomial, if I expand all of its factors, all of its linear factors, I'm going to end up with something ax, anx to the n plus dot dot dot, etc. If I write them in decreasing order. And the leading term is going to be ax to the n, okay? And the coefficient of the next term, the coefficient of x to the n minus 1 is just going to be an times r1 plus r2 plus r3 all added together. And there's going to be a negative sign in front. And why is it going to be that? Well, the way I get x to the n minus 1 when I expand these brackets is by choosing x in one of the braces and all of the r's in all of the other brackets. So, sorry, I'm choosing x n minus 1 times, which means I have to choose x, x, x. And if I have x to the n minus 1, it's because I chose r, or one of the constants, in exactly one of the braces and no more, okay? And because I can do that in every brace, when I expand it, all the terms that give me x to the power of n are just the terms that correspond to having chosen each constant term once. And let me show you an example of that in x minus 1 times x minus 2. Okay, when I expand that out, I'm going to get x squared minus x, then minus 2x, sorry, then minus x, and then plus 2. The terms that multiply x came from just doing minus 2 and minus 1, right? Because the only way I can get x to the power of 1 is by choosing x in one bracket and the constant term in the other bracket. And in general, if I have this long expansion, the only way to get x to the n is to pick x, 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 n minus 1 times, and pick r one time, okay? And because there are n r's, there are n ways to do that, and I'm going to have to add them all together. And the minus sign is just a consequence of the fact that each of these has a minus sign in front of them, okay? So what does that mean? It means that if I were to add up all of my roots, r1 plus r2 plus r3, etc., it's going to give me the second term, the coefficient of the second term divided by the coefficient of the first term with a minus sign, right? So that's this formula here. It's in your formula booklet, right? The sum of the roots is negative a sub n minus 1 over a n. And I can do something similar for the product by considering what happens when I expand out the brackets. Well, the constant term comes from multiplying all of the r's together with no x's. So I've done r1, r2, r3, and that's just going to be multiplying an. So the constant term is going to be an times all of those negative roots multiplied together. And because there's negative signs, I have to put this minus 1 to the n, an times the product of all of the roots. And if I isolate this product of roots, I'm going to get a0, the last coefficient, the coefficient of the constant term, divided by an, the coefficient of the leading term, times minus 1 to the power of n. Okay, now you don't really need to know how I derive those formulas. I included it there just in case it was helpful for your intuition. All you need to know is how to apply these formulas, and they're in your booklet. So let's do an example. Let's suppose I have the polynomial 8x squared minus 2x cubed minus 2x minus 12, okay? And I'm told that it has a root at x is equal to 2. And I want to express p as a product of linear factors, all right? So let's first put the terms in decreasing order. I have negative 2x cubed plus 8x squared minus 2x minus 12. The sum of the roots is 4, because I do 8 divided by negative 8 divided by minus 2. That gives me 4. And the product of roots is going to be negative 1 to the power of 3 from the degree times negative 12 over minus 2. And that gives me minus 6. Right? And I know that one of my roots is 2, so I can write, if the two unknown roots are alpha and beta, I can say alpha plus beta plus 2 is equal to 4, and 2 alpha beta is equal to minus 6. It follows then that if I let alpha equals to minus 1 or 3, it follows by solving this that alpha is equal to minus 1 or 3, which means that beta is 3 or minus 1. In either case, the roots are just going to be minus 1, 2, and 3. And if I just remember that I have a minus 2 in the polynomial, I can factor it as minus 2 times x plus 1, x minus 2, and x minus 3. Okay? I think I have a quick example for you to do. I'm going to give you 30 seconds to do this. All right, let's take a look. So I have a quartic polynomial, which has a degree of 4, so n is equal to 4. So the sum of my roots is going to be negative 9 over negative 3, which gives me -3. That is the sum of my roots. And then the product of the roots is just going to be, I shouldn't have skipped that. The product of the roots is going to be product is -1 to the power of 4, because that's the degree, times 12 over -3, and that's just -4. Okay? -4. Perfect. It seems like most of you got that right. Okay, so with that said, let's do an IB style example. I'm going to give you 5 minutes to do this on your own. All right, let's go over the solution to this. So in part A, I'm asked to verify that x plus 2 is a factor of p of x. So x plus 2 is going to be a factor if p of -2 were equal to 0. So let's check. P of -2 is 5 over 2 times -2 cubed minus 4 times -2 squared. -27 times -2 is plus 54 minus 18. Okay, the -2 cubed is 8. So that's going to give me -5 over 2 times 8 is -10. Or, yeah, -20 even, sorry. -20. Then I'm going to have minus 4 times 4 is -16 plus 54 minus 18. What does that give me? 20 plus 16 is 36 plus 18 is 54. So -54 plus 54 is indeed equal to 0. Okay, and that confirms that x plus 2 is a factor. Boom, that's part A. Now in part B, I'm trying to find the two other roots of p of x. Okay, now what I can do is I can write down that the sum of the roots is going to be -4 over 5 over 2, which is 8 over 5. And the product of the roots is going to be -1 to the power of 3, because I have a cubic polynomial, times -18 over 5 over 2. And that is going to give me 36 over 5. Okay? Now, what do I know? I know that I have a root of 2, -2 even, and that I can call my other two roots alpha and beta. And that means that alpha plus beta minus 2 is equal to 8 over 5. And alpha beta times -2 is equal to 36 over 5. Okay? That is pretty useful. Now, what can I say next? I have to solve this system of equations. I'm going to turn this into, I'm going to add 2 to both sides. Alpha plus beta is equal to 18 over 5. And alpha beta is equal to -18 over 5 if I divide by 2 on both sides. Okay? Now, I think most useful, or like the fastest way to solve it once you have this out, once you know the sum of two roots and the product of two roots, is to remember that this means that these are going to be the roots of the quadratic x squared minus 18x, 18 over 5x, minus 18 over 5. Now, why is that the case? Well, because a quadratic, remember, the sum of its roots is negative the second term divided by the first term, and the product is the third term divided by the first term. So if I let the first term just be 1x squared, then I can simply write for any known sum and product of roots. If I have the known sum of 2 and the product of 2, I can just solve this quadratic. And I can turn it into a quadratic that has only integer coefficients, and that's going to make my life a little bit easier. So let me do that. And what do I get? I'm going to get 5x squared minus 18x minus 18 is equal to 0. All right. And now I would like to try and actually I can't factor that. It's not going to be a nice numbers, but I can use the quadratic equation and say it's going to be x equals to 18 plus or minus the square root of, and now I'm going to write 18 squared minus 4 times 5 times -18. And I'm going to leave it like this for a moment so that I can simplify as much as I can. Okay, so it's going to be all divided by 10. Now, under the square root, I have 18 squared and then plus 20 times 18. So in total, I'm going to have 18 plus or minus the square root of 38 times 18. because I had 20 18s. I had 18 18s and then another 20 18s. And so I can now divide that by 10. And the square root of 18, actually, I can rewrite that a little bit better. This is all over 10. I can say it's equal to 18 plus or minus the root of 19 times 36, all divided by 10. And that's going to be perfect because 36 is a perfect square. So this is, I keep writing 2, it's over 10. This is equal to 18 plus or minus 6 times the root of 19 over 10. And that is my answer. And you can simplify if you want. We can say 9 plus or minus 3 root 19 over 10. That's like as much as we can simplify. Over 5 even. Hello, go away. 9 plus or minus 3 root 19 over 5. Okay? That is my final answer. Those are the two other roots of the polynomial. Any questions about this? I'm going to check. And the conjugate root theorem says that if a polynomial has real coefficients, which in the IB, except on paper 3, maybe, it will basically always have real coefficients. So that means I can write it, 2x cubed plus 5x squared, something, 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 and not, ix to the 5 minus 2 plus I x. As long as there's no complex numbers in there as the coefficients, then there's going to be no problem. And when that is true, if I have a complex root of a polynomial, if a plus bi is a root, then a minus bi is also a root. And I'm not going to waste the time or spend the time showing you the proof of that, except to say that if you imagine having a complex root, but not its conjugate, then imagine what happens when I add up the roots or when I multiply the roots together. I need for all the coefficients to be real, for the complex root to cancel, and I can do that by making sure that its conjugate is also a root. Okay? A consequence of that is that a polynomial with an odd degree must have at least one real root, because all complex roots come in pairs. If I have one root, I have the conjugate is also a root. So if I have 3 roots total, then I can't have 3 complex roots because I have to have an even number of complex roots. Okay, so this is something that I think showed up once on the old syllabus as like a 1-point question. Explain why this polynomial must have at least one real root. And it was about this whole thing with complex pairs, but it hasn't shown up on the new syllabus. Theoretically, it could. Okay, here's an example. I have the polynomial z cubed plus 3z squared plus 7z plus k, and it has a root of 2i minus 1, and we want to find the value of k. All right, if 2i minus 1 is a root, then negative 2i minus 1 is also a root. And I can tell by looking at this that the sum of the roots is minus 1. And if I add these two things together, I'm going to get minus 2, which means that the real root has to be minus 1. Okay? And then the product of the roots is just negative k. It's negative 1 to the 3k over 1 is negative k. And if I multiply everything together, I have minus 1 times 2 minus I times negative 2i minus 1. That's going to give me negative 5. So k is equal to 5. All right. Okay, let's go over the solution here. I am considering the polynomial x to the 4 minus 6x cubed plus 13x squared plus 6x minus 104. The first thing I want to do in part A is write down the sum and product of the roots. So the sum of the roots is going to be negative 6 over 1, so that's just 6. And the product is going to be negative 1 to the power 4 times negative 104 over 1. That's negative 104. All right? So that's part A. Now, in part B, I'm given that P of 2 plus 3i equals 0. That means that 2 plus 3i is a root. And as a consequence, 2 minus 3i is going to be a root. That's what the conjugate root theorem says. And that means that 2 minus 3i is a root. Okay? So 2 minus 3i is a root. Now, that means that I'm going to be left with 2 unknown roots. Let's say that they're alpha and beta. So I have alpha, beta, and 2 plus or minus 3i are my roots. Now, I already know the sum and product of the roots, so let's add up what I have. If I do alpha plus beta, then plus 2 plus 3i plus 2 minus 3i, that's supposed to be equal to 6. That's going to give me alpha plus beta plus 4k. can't write today. Plus 4 is equal to 6. And that means that alpha plus beta is equal to 2. Okay, so that's one equation. What else do I have? I know that the product of the roots is alpha, beta, 2 minus 3i, 2 plus 3i. So remember, a complex number times its conjugate is just the modulus, so it's going to be the modulus squared even. So alpha, beta times 2 squared plus 3 squared, and that's supposed to be equal to minus 104. And 2 squared plus 3 squared, well, that's going to be 13, okay? So alpha beta is equal to negative 104 over 13. And I can do that by remembering that 130 is 10 times 13. So 104 is negative 8. So this is negative 8. It's 8 times 13. Okay? So alpha plus beta, alpha times beta even, is equal to minus 8. Now, I have two roots that add to, and hang on, I have a question here. As the maximum power is 4, how are there only 3 roots? There are 4 roots. It's just that I have a 2 plus or minus. So that's 2 different roots. Okay? So I have alpha plus beta is equal to 2 and alpha times beta is equal to minus 8. That defines, or is equivalent to solving a quadratic, x squared minus alpha plus beta x. I could have written that beta better, so let me just fix that. Alpha plus beta x plus alpha beta is equal to 0. So I'm trying to solve the quadratic x squared minus 2x minus 8 is equal to 0. All right, let's use, I'm actually going to factor this by inspection. I'm looking for two things that multiply to minus 8 and add to 2. I can do x squared minus 4x, sorry, x minus 4 times x plus 2. I can just do it directly. And that means that I have alpha is equal to 4 or 2, or beta is equal to 2, and this is supposed to be minus 2 or 4. You can have them either way. It doesn't really matter because alpha and beta are, there's no relationship between them. We don't know which one is which. But we do know that overall now our roots are 2 plus or minus 3i and negative 2 and negative 4. Now, the question is asking us to factorize this fully. Okay, so we're going to have to do that. 2 plus 3i is a root, then 2 minus 3i is a root, right? So I can write at least one of the factors as x minus this times x minus that, okay? And that's going to be x squared. Then it's going to be plus x times the sum of those two roots. And the sum of a complex number and its conjugate is just going to be twice the real part, so it's going to be minus 4x. And the constant term is going to be plus the magnitude squared, so plus 13. Okay, so that is one of the factors. And then the other factors are just the x minus 4 and x plus 2 that we found. So this is my answer, my fully factorized polynomial. If we factorized as x minus 2 minus I instead of the quadratic, would that also be valid? Yeah, probably in this question it would be. I might have, maybe I could have phrased this question better and said, yeah, but in either case, both would be fine because you factorized one step further. And I think probably, honestly, I should change the wording. The way that IB would ask this question is more find all the roots of P instead of factorize fully. Usually they say factorize fully when you can actually factorize into linear terms like this, and then they'll say express P of X as a product of linear factors. That's what they would say. But in this case, I couldn't say that because that's not a linear factor. Okay, that's a good question. It'll always be clear, and if it's not clear, then they'll accept both. I mean, people think that the IB is like really annoying about grading, and they are for things like induction and proofs. They want you to write things a certain way. But if they wrote a question that's like slightly ambiguous, the mark scheme always has a little note in there that says, "Oh, we also accept this." That was the last question that I wanted to cover today. What I want to talk about now, briefly, is the graphs of polynomials. And, this is a weird one that is technically on the syllabus, but it hasn't really shown up as far as questions go in any real way in the new syllabus at all. Like, there hasn't been a question where you need to know this stuff. I'm putting it in there in case it does show up for you, but I don't have any problems because they haven't showed up, and I haven't really made any because I'm not convinced that it is going to show up because it's a bit of a weird skill. okay? But one thing we know is that if the coefficient of the leading term, that's going to determine the broad shape of the graph, okay? So if a is positive, then in general, I'm going to have either the whole thing is concave up if I have a even polynomial, or it's going to be generally increasing except for some weird stuff that might happen in the middle. And it's going to be the opposite if I have a less than 0, okay? Now, I also know that the x-intercepts, or the factors that I found for my polynomial, will correspond to x-intercepts on the graph, all right? Now, in particular, the graph is going to behave in different ways depending on whether my root repeats or not. So if I have a factor of x minus 1 squared, then I am going to have a root at x is equal to 1, but because x minus 1 squared is always positive, I'm not going to cross the x-axis at x is equal to 1. Instead, I'm going to have something that looks like this. I'm going to have this even repeat where the graph comes tangent, but then goes back up again, or goes away from the axis again. Now, if I just have a single root that is not repeated, I'm going to cross the axis. I'm going to change sign, and there's going to be no repeat. Now, the other case is when I have x minus 1 to the power, I have, some root that's repeated an odd number of times. So let's say it's repeated 3 times. Then I'm still going to have that, like, let's say I have x minus a cubed. I'm going to have x minus a times x minus a squared. And I'm still going to have this square term that makes the function smooth at 0. And it makes it smooth because when I have a small number and I square it, it gets smaller. Rather than crossing abruptly, you get this very smooth behavior. But I am going to have a sign change because x minus a is going to change signs here at a. So an odd repeat is smooth, but it does cross the x-axis. So this is kind of like, we have a question. This would more likely tie in with questions on maxima, minima, and inflection points. I mean, yes, sort of, but the thing is, as soon as you're doing questions about maxima and minima and stuff, you have the derivatives already. And so you almost don't need to know this stuff about polynomials. The way I could see this showing up on an exam is like essentially as a paper 3 type question where they essentially give you, I don't know, they might say something like, imagine you have a polynomial of the form x minus 1 to the power of a, and then x to the power of b, and x plus 1 to the c, or something like that. And they might have you explore what happens when a is an even number, when c is an odd number. I don't know. They might kind of mess around with the idea, but they would probably like kind of scaffold it a lot. That's how I would see this showing up on an exam, because it is like, you can figure this stuff out sort of, but it is very, very subtle. And it hasn't been examined yet. It's not something they seem to expect you to know. It's something that they do want you to know, though. So I could see it showing up on a paper 3. All right. So if there are any questions about this, I'm happy to go over it more. Otherwise, that is everything I wanted to talk about in polynomials. It's a pretty easy session. Like I said, we've done all the material. There are more problems on the website that you can check out if you're still not 100% comfortable.